Good afternoon. My name is Tang. I'm from Columbia University. Today, I'm going to talk about UNIC, a system that lets applications securely deduplicate their computations. This work is in collaboration with my advisor, Professor Junfeng. The world's data has been fast exploding for many years. This massive amount of data comes in greatly varying forms, like photos, videos, source code, binary programs, or data collected from sensor networks. It poses great challenges for storage provisioning and management. Fortunately, a significant portion of the data is redundant, and data deduplication can hugely save storage and simplify management. It detects when multiple files have the same data and stores the unique data only once. However, not only is the data redundant, but the computations on top of the data are also redundant. The redundancies are actually everywhere, from local workstations to cloud computing servers. For example, a user may scan her Dropbox files for viruses, while another user runs the same virus scanner on a similar set of files. With the same input file, the same deterministic antivirus algorithm always produces the same result. So the question is, can we deduplicate computations as well? Since computations are typically slow, it would be more efficient to memoize and reuse the results rather than redoing the whole computation. But there are many challenges in doing that. The biggest challenge is how can we deduplicate computations done by users who don't mutually trust one another? Of course, we don't want anybody to be able to put a wrong result in the cache. So let's take the example of different users scanning their Dropbox files for viruses. Think about it. What if a malicious user marks a file as safe, even if it contains a virus? Pretty bad, huh? In addition, we also don't want anybody to query the cache for any information that she shouldn't know. For example, a user who doesn't have the antivirus application shouldn't be able to know if she has some files has viruses, even if some other users has cached the virus scanning result. And what's worse, the access control systems don't help much here, because these people may be perfectly legitimate Dropbox users like you and me. They are authenticated for logging into their Dropbox account. But do you trust them for their computations? Probably not. Our insight here is that we don't actually authenticate the users. Instead, we only authenticate the computation itself. Therefore, UNIC's way of solving this problem is leveraging code attestation to achieve both integrity and secrecy. However, our challenges are more than that. Another big challenge is how can we deduplicate general computations? Virus scanning is just one of the millions and millions of things you can do. The computations on top of the real-world data are much more diverse. Maybe some people are compiling the Linux kernel source code, or compressing a large video file, or running some big data analysis over the public data sets on Amazon Web Services, such as building an inverted index for web pages in Common Crawl. All these computations are perfect candidates for deduplication. However, it's impossible for us to understand every one of them. Existing tools such as Ccache or Nectar can only handle very specific computations, mostly because they don't modify the applications. Our insight here is that if we allow the application developer support to slightly modify their applications, we can deduplicate much, much more. Therefore, UNIC provides a simple yet expressive API in order to let application developers deduplicate their own rich computations. It's general enough so that pretty much any application can use it. Now, before we dive into the details of UNIC's design, let me first give you an overview of UNIC. UNIC is a system to let applications deduplicate their own computations. It's both general and secure. The application uses the UNIC API to cache computation results. The first time someone does a computation, UNIC puts the result into the result cache. And later, for the same computation, UNIC reuses the previously cached result. The biggest novelty here is that UNIC leverages code attestation to achieve both integrity and secrecy. So next, I'll talk about UNIC's security design. I'll then show you an example of how an application would use UNIC. After that, I will describe the UNIC API and show some evaluation results. So now let's start by looking at two major threats to UNIC. The first threat is cache poisoning, which means that a malicious user may try to hack an application to put wrong results to the cache. In our antivirus example, it means that someone wants to mark a file containing virus as safe. The second threat is query forging, which means that a malicious user who cannot do a computation may try to forge a query to get the computation result from the cache. In our antivirus example, it means that someone who doesn't have access to the antivirus application wants to know if a file contains viruses or not. The good news is that UNIC prevents both attacks by using code attestation. So now let's see what code attestation is and how it works. First, what is a computation? A computation is just running some code on some input to yield the result. In our antivirus example, the code is the virus scanning function. The input is the file, and the result is whether the file contains viruses or not. Okay, then what's code attestation? Code attestation is a mechanism that cryptographically binds the result with the code and input that generates the result. It gives us a signature that anyone can use to verify that the whole computation is intact, including the code, input, and the result. This signature cannot be forged, which means if you change the computation code, or if you change the input or result, then you won't be able to get the correct signature. There are different ways to realize code attestation, which is orthogonal to UNIC. And for practical reasons, we assume that the operating system is trusted. But this assumption could be lifted with hardware support, such as Intel SGX. Okay, so now let's come back to see how UNIC uses code attestation. UNIC computes two things. First, it runs the code on the input to compute the result. Second, it computes the hashes of the code and input, concatenates them together with the result, and computes the HMAC of it with a secret key. This key is distributed among the trusted operating systems. It can either be symmetric or asymmetric. So this HMAC is our signature for code attestation. We can see that it binds code, input, and result together, and it's non-forgeable due to the cryptographic properties of HMAC. Next, let's see the protocol between the application and the UNIC cache. When the application wants to compute code on input, it queries the UNIC cache with the concatenation of the hashes of code and input. If the cache hits, then UNIC returns the result to the application, and the computation is done. However, if the cache misses, then the application needs to compute the two things that we just showed and send the newly computed result together with the signature to the UNIC cache. Then, UNIC validates the signature and updates the cache entry. And here, I'd like to emphasize two things about this design. First, someone must know both the code and the input in order to query the cache. So it prevents query forging attacks, because with code and input, she can perform the computation on her own anyway. And second, since the signature attests the whole computation, it also prevents cache poisoning, because suppose someone modifies the application code, then either the cache entry is different or the signature is wrong. In any case, she cannot poison the cache entry belonging to a legitimate application. So this is UNIC's security design. And next, I'll show you an example on how an application would use the UNIC API. Here is an example of a very simple virus scanning application akin to the open source antivirus tool ClamAV. This piece of code reads a file into the buffer, calls the scan signature function to scan the buffer for viruses, and prints the result. The parameter options is passed through to the virus scanning engine. The scan signature function is CPU bound and very expensive. So now, suppose another user wants to scan the same file for viruses. This function has to be executed again. Now, let's see how the developer can modify this code to deduplicate it. With the UNIC API, it's actually very easy and natural. Since UNIC keeps the result in the result cache, instead of running the scan signature function all the time, we call the UNIC API function exists to see if UNIC has seen this computation before. If not, we run the scan signature and put the result to the result cache. Now, suppose a second user wants to scan the same file. This time, we can simply get the result from the result cache without running the scan signature all over again. Now that we have deduplicated the scan signature function, here comes another bottleneck. The read is a time-consuming I/O operation, and we are doing it all the time, regardless of whether there's a result in the result cache. Unfortunately, the operating system's buffer cache is not enough, because by the time we see the redundant computation, the buffer cache may be gone, or the computation may not even happen on the same machine. UNIC has a better way to solve it. Since the underlying storage system may already know what files are duplicate, UNIC explores a cross-layer design that allows the underlying storage system to expose data deduplication information to the application. Specifically, we replace the read with another UNIC API function, getFileHash, and use this file content hash instead of the actual file content to query the result cache. The difference here is that the storage system, such as ZFS, already keeps the hash of the file content as a metadata for data deduplication purpose. So getting the file hash doesn't require the heavy I/O. We only read the actual file content if the hash is not in the result cache and we really need to do the computation. So therefore, with UNIC, we have avoided both the CPU-intensive scan signature function and the I/O-intensive file reads. To sum up, UNIC provides this API to let applications deduplicate their own computations. It's very easy and natural to use. The application calls init once at the very beginning to initialize UNIC. Next, the getFileHash function gets the hash of the file. It automatically leverages the deduplication metadata from the underlying storage system, so it doesn't actually read the file content. In addition, we also provide a function to leverage storage deduplication at block level. For that, please refer to our paper. Finally, the exists, get, and put functions query or update the result cache. The parameter ID is an optional string identifier defined by the application, which is used for differentiating multiple computations performed on the same input. For example, our previous antivirus application was using the scanning options as the ID. So this is the UNIC API. And next, I'd like to show you some evaluation results. Our experiments aim to answer 3 questions. First, is UNIC easy to use? Second, does UNIC reduce computation time? And third, what is UNIC's storage overhead? We evaluated UNIC on 4 open source applications. ClamAV is an antivirus software. PBZip2 is a multi-threaded compression utility. grep is a pattern searching tool. And finally, we have the GCC compiler. We picked these 4 applications because they are popular, and in practice, we are doing a lot of redundant computations with them. So first, let's see the effort for adapting each application to use the UNIC API. This table shows the number of change lines. For all of them, the change is fewer than 1%, so UNIC is easy to use. Next, let's see the application performance. Our datasets include the Linux source code tree, the CTEX file generated from it, and my personal Dropbox folder with over 10 gigabytes of files. We show the relative running time for each application using UNIC versus without using UNIC. Here are the results. The blue bars are for running the applications for the first time when the result cache is empty. The overhead mostly comes from writing to the result cache. This circled one has a big overhead because the original computation was fast enough even without using UNIC. And in this case, UNIC has an optimization to reduce the overhead. Please refer to our paper for details. The green bars are for running the applications with the result cache when the result cache has already been populated. We can see that reusing the cached results is much faster. The average speedup is 7.6 times. Therefore, UNIC can indeed reduce computation time. In the next experiment, let's see whether UNIC works well if the input data is not exactly the same, but changing over time. This resembles a more practical scenario since the computations are only partially duplicate. In this experiment, we run grep over a series of 13 major versions of the Linux source code. The y-axis in this graph is the running time. This blue line is the baseline where we run the original grep application without UNIC. This green line is the running time for the UNIC-enabled grep application, where for each data point, UNIC has cached the result for the computations against the previous version. On average, we still get a 1.5 times speed up versus the baseline. And therefore, UNIC is also working well with partially duplicate data. Finally, let's see UNIC's storage overhead. This table shows the dataset size and the cache size for each workload. We can see that the cache size is only a fraction of the dataset size. Therefore, UNIC incurs little storage overhead. To conclude, we presented UNIC, a general system for applications to securely deduplicate their rich computations. It uses code attestation for secrecy and integrity, explores a simple and expressive API, and explores a cross-layer design to leverage storage deduplication. We believe that deduplicating computations should be both easy and secure, therefore helping applications survive and thrive in this big data world. Thank you, and I'm happy to take questions.
Hi, this is Dan Ellard from Raytheon BB. This is really interesting stuff, and I think it has a lot of promise. But it may be just because this is a high-level talk and you're not going into details, but I noticed there was a time of check to time of use bug in when you take the hash of the file and then later on you use the file. Do you have some primitive to make sure that the file hasn't changed out from underneath you in between those two times?
Thank you for this question. The thing is, actually, we rely on the developer support for using UNIC API. So if the application is prone to this kind of stuff, the developer should use a lock or something to protect the critical region. Okay. So, yeah.
I have another question, but I'll let other people go first.
Jeff Kenning, Harvey Mudd. I missed something here because the application calculates a result, and then it sends an attestation that says, I used the following function on the following file, and I got the following result. But I don't see where there is any guarantee that the result came from the function that I claim to have used. I could have taken your sample code, and immediately after you said result equals scan signature, I could insert another statement that says result equals virus free, and then send that off to your server, and it seems to me that your server would happily accept that result.
So this is actually not possible with code attestation. Actually, code attestation is orthogonal to this work. So in our implementation, because we trust the operating system and everything below that, we can guarantee that this kind of stuff cannot be done. But if you are really serious about that, you may have some hardware support to maybe give you a sandbox for the whole computation and make sure from the beginning to the end of the computation can never be touched by anybody. With that, this is perfectly secure. And I think there was previously proposal work from other people doing that for code attestation. So with that, I think UNIC is secure in these terms.
Hi, Fred Douglas, AMC. So if you have something where it changes slightly, so the hash doesn't work and it tells you it's new and you have to start over, then you're losing all the benefit of this, right?
That's right.
So is there anything you can do to support some notion of transitive operations where, if you think about, I don't know, let's say your operation were word count and you were accessing, operating on a particular file, but you could actually use all the work you've done before on one piece of data and then add to it something else. Could you support that kind of transitive property?
So first, we currently don't support the transitive property for computations, but for files, we actually support block-level deduplication. So if, for example, you have this kind of application that 90% of the file are the same and only 10% is different, then we can still reuse the computation result for the 90%.
And how does it know that it's okay to do it at block level? You have to tag it that way explicitly?
Again, it's because we leverage the application developer support. So the developer, if the developer thinks it's possible, then it can do that.
Hi, as a follow-up to the question before about how you know what code is submitting the result, I looked in the paper and you mentioned that you take a signature across a statically linked binary. Mm-hmm. So your code hash is now the binary itself and the kind of transitive closure of everything it might need.
Yeah.
And this means that the code hash is going to be very fragile to changes in environment. There's also a deployment difficulty if I want to ship this to my customers. Do you have any thoughts about how you might reduce the size of the code signature or be able to handle, a mobile app and a desktop both submitting the same computation and having it cache?
So this is actually a very good question. And I think this work is the first along this series, and we currently don't have anything related to that. But it's definitely a very interesting future work for that. Thank you.
Thank you.
I had a similar question, but I'll make a comment instead.
Mm-hmm.
My question was, how much of the platform do you hash? It sounds like that's answered in the paper. But I wondered if you could have hierarchical hashes where you could say, this is the hash of the binary, this is the hash of the libraries that I used, this is the hash of the operating system I used. And then you could have a knob that determined, which ones of those you needed to be the same in order to compare the results. Some applications it might be just one, others it might be all.
Yeah, thank you for the comment. It's actually good. So in our work, we currently, because we trust operating systems, we don't include the cache for the OS. And also we require the application to be statically linked. So that solves the problem for this one. But I think what you mentioned is definitely a good point to do.
Thank you.
Yeah, thank you.